Hey everyone, welcome back, and today let's solve Leetcode problem 827 titled Making a Large Island, a classic and very good matrix problem to solve. So relatively at least a pretty simple and concise problem statement here, a very good problem again. We're given an n by n binary matrix, it's called grid, and we're allowed to change at most 1, 0, or basically one cell that has a value of 0 to be a 1, and we need to return the size of the largest island in the grid after applying this operation. Now, why do we want one cell of 0 to be switched to a 1 to get the largest island? Well, because an island is simply a four-directionally connected group of ones, right? That's basically what we're trying to maximize the size of in this case, after changing a 0 cell, which is a water cell for the context of this problem, to an island cell, or rather a land cell. So in example 1, we have our input grid to be 1, 0, and 0, 1, a 2 by 2 matrix, and in this case, our output is 3. The reason why is because we can change one of these two zeros and basically just change it to a 1. Once we do that, we can actually connect the two ones, and then we'd get an island with area 3. Right, we'd have this one here, and then these two ones here. Or we'd have this one here, and then these two ones here after changing this or this 0 to a 1, right? And to kind of visually represent that, as you might have an array like this is going to be a little bit hard to demonstrate, but let's just say I have 0. Sorry, let's just say I have 1 and then 0, and then I have 0 and then 1. Pretty bad drawing here. Hopefully you guys understand it. In fact, I'll just delete this for now. Don't think we need it as such. Right, so we have this, assume this is our 2 by 2 matrix, we have 1, 0, 0, 1, like the problem has given us. In this case, if we changed either this 0 to a 1, or we change either this 0 to a 1, either way, we would have a fully connected island of 3 now, right? That would be the maximum area, and so that would be the output that we have, right? We'd get a resulting island of a maximum land area of 3. And notice how in that scenario there, all of the ones were four-directionally connected. And what they mean by four-directionally connected to one another is basically they're connected in either one of the four cardinal directions, either north, west, south, or east, or up, down, left, or right. Right? These two ones are connected vertically. These two ones are connected horizontally. Right? So, as you can see, that's the reason why we have an output of 3. For example, 2, we have a grid to also be the same dimensions, 1, 1, 1, 0. And in this case, our output is actually 4. So very similar to the previous example here, except we're actually given the input matrix in form like this. And we know we can change at most 1, 0 to be a 1. Well, the obvious answer would be to change just singular 0 to be a 1. And if we did that, this entire input would be an island by itself. It would have an array, or rather an area, of 4. That would make the island bigger. Basically just one dense island by itself as the entire matrix or entire input with an area of 4. Right? And a nice way to calculate the area, simply count the number of ones in that area. Right? In this case, it's a little bit simpler of a formula. It'd just be 2 times 2. But if we had something like this, well, then we could simply just count that we have 3 ones in this four-directionally connected island. That's the reason why we have an output of 4. Right? That's the max area that we can actually form. And for example 3, we have our grid to be 1, 1, 1, 1. In this case, not only do we not need to change any zeros in this grid to a 1, we can't change any zeros to this grid to a 1. And the reason why is because we don't even have any zeros in the first place. We're already given this input as one entire input matrix. It's an entire island itself. It has all ones, and so we simply have to output its area of 4. We can't increase the island because all of these cells are already land cells, forming the largest possible island possible, right? So that would be an output of 4. So obviously, as we can see, the output cannot actually exceed the area of the entire grid because, of course, we can't have more cells than we have cells in the grid. That wouldn't be logical, right? So that's just a quick observation to make. That isn't really the main one for this problem. But for the constraints here, we see that n is going to be the grid.length and grid.I.length, which really just means the number of rows and columns in the input matrix. And we see that those values, n, are going to be within 500 and greater than or equal to 1. And we are also given that grid.ij is guaranteed to be binary, meaning it's either 0 or 1. And for the context of this problem, to make it a little bit simpler to understand, it's either going to be a water cell or a land cell, right? Either a 0 or 1. Of course, 1 are the cells that we're trying to actually target to maximize our island size. right? So with the problem statement, constraints, and examples out of the way, I will give you guys a few seconds to just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so how can we kind of really optimally solve this problem? What is kind of a high-level rundown of the solution that we're going to take? Well, like we do for most matrix/graph problems on Leetcode and data structures and algorithms in general, we're going to use a variation or just a direct algorithm implementation of either DFS, depth first search, or BFS, breadth first search, to solve the problem, right? In this case, either one really works, and effectively how we're actually going to use the algorithm. Basically, first we're going to find all of the islands in the input and simply label them uniquely. And then we're actually going to be using a DFS or a BFS, whatever you want to kind of use, to actually traverse the grid and assign that specific unique ID or kind of label, if you will, to each island that we find. And we can do this recursively, of course, using either BFS or DFS. And as we actually traverse the input, we'll basically just calculate and store the size of each island in a hash map or dictionary data structure. Okay, fine. Once we actually get all the island sizes and their unique IDs of the number of islands we have in our input, now we actually want to store our computed island sizes, right? And how can we do that? Well, basically, in the hash map that we'd add the actual island size to in the dictionary, the key would be the island ID, and the value would simply be the size of that island, right? It would be the key island ID being mapped to the key value pair of its corresponding size for that specific island key. And then, once we actually fully store all those islands with their corresponding IDs and sizes in the input, or rather in the actual data structure hash map, then we actually have to check each water cell for the context of this problem that I'm just going to be calling 0, right, and actually compute the potential new island size after changing it, after actually potentially applying the operation on that specific water cell, right? Effectively, the way we can simply do that is for each 0 or water cell in the input, we'd first check its neighboring islands and simply sum up the sizes of the connected islands, and just while we're actually simultaneously doing that for all the valid water cells that we can switch, we track the maximum possible island size and effectively return that maximum possible island size. But however, if there are no zeros in the grid, well then the whole grid would already be an entire island by itself, and we simply immediately return m times n. Of course, because that would be the number of cells we'd have in a grid, that would be the maximum area of the number of cells that we have as an island in our input. Right? So now let's actually get into the actual code here, now that we're done talking about the high-level rundown. So again, what I usually do for problems is actually get the number of rows and columns for easier traversal and initialization for my input matrix problems. In this case, we're given that n and m, the number of rows and columns generally, are the same. And so I can literally just get n to be the length of the grid, or length of the grid at index 0. I'll just do length of the grid for simple. This n is not only going to mark the number of rows, but also the number of columns. Why? Because both the number of rows and columns are equal to n. It is given that we're going to have an n by n square binary matrix, right? It's binary, and it is also a square matrix. Great. Once we actually get those values, now let's actually initialize our hash map and our unique island IDs. So as I just talked about, I'm literally just going to call them island ID and island sizes, as you may have imagined. And island sizes would, of course, be initialized to an empty hash map. I don't know why a period got there. Sorry about that. And the island ID would actually be initialized to 2. I'll explain more on that a little bit more. And first of all, I want to actually get into what we actually initially populate or initialize these island sizes with. It would actually be initialized with 0 corresponding to 0. All right, let me get into why that is in a bit. First of all, why is island ID actually equal to 2? Well, the reason why it's equal to 2 and not like 0 or 1 is because we want to actually label the islands uniquely starting from 2. 0 is already water, and 1 cells are already land in the original grid, so we'll start from 2 and label our unique ID islands correspondingly starting from 2 and going incrementally forward. Now, why do we initialize this island sizes with 0 and 0? Well, think about it. What did we say that hash map would do previously? Well, it would be storing or mapping the island ID, the unique island ID, with its corresponding size. Well, we know that water, an empty cell, or rather not an empty cell, but a water cell, 0, would contribute exactly 0 to any island. It would have a size contribution of exactly 0, right? And again, this is the hash map that simply stores these sizes of different islands mapped with their corresponding IDs. Water, or 0 cells, would contribute 0 to any island. And so that's how we initially populate this island sizes, 0 mapping to 0. Now, you don't have to actually do this next part of this code and the solution here. You can technically do it using a conditional, or rather even a recursive call. But I am going to do this mainly because it's a little bit easier to actually iterate through and call for neighboring nodes. And I'm going to do something called initializing a directions array. Right, and the way I usually initialize this is simply just an array of tuples of length 2 with all the coordinate offsets that we can actually travel for neighboring nodes from the current node. And the way we would do that is simply have the node for the up, down, left, and right nodes for the neighbors. So that would be 0, 1, 1, 0, 0, -1, and -1, 0. Right? Simply just the coordinate offsets or the coordinate offsets of all the neighboring nodes to actually help us traverse up, down, left, and right in the grid from any current given node possible. Okay, well, now let's actually start to define and implement that DFS helper function, that recursive call helper function. So, the way we're going to do this is simply like we usually do for DFS problems. I'm literally just going to call it DFS. And for the parameters, we're going to be taking 3 parameters. We're going to be taking the row and column value, basically the cell value of the current cell that we're at in this execution or call for this function. And also we're going to be taking in the island ID. So I'm literally just going to call it island ID. It's going to be the unique island ID that we actually label that specific island. And R and C are going to actually be the nodes or coordinate cell values to help traverse from that specific cell. Well, now let's actually move on to the standard base case that we have for our recursive DFS function. In this case, it's going to be if we don't have a land cell, meaning we have a water cell, or we go out of bounds, right? So the way we can do that in Python, it's a bit lengthy, but it still has similar logic as all the other languages. If R becomes negative, or C becomes negative, sorry, should be an or C becomes negative, or our R or C values exceed the number of rows and columns we have respectively, meaning R is greater than or equal to N, or even C is greater than or equal to N, we have a cell value that's more than the number of rows and columns we even have in the first place, or the special base case in the context for this problem, granted the current index RC, it's not even equal to a land cell, meaning it's not equal to 1. If any one of these conditions are true, we know we can immediately set graded RC to simply be the island ID. Right? But before we actually do that, we want to actually have the return statement for this base case. Now, what would that be? Well, this is the base case to check if our current cell is invalid, right? Either it goes out of bounds or it's a non-land cell, meaning it's actually a 0. The moment we actually encounter a cell that does that with index RC, we know we immediately have to return 0. Right, we immediately have to return 0. That's the base case, and we simply just move on to the next call. We don't even do anything. We don't even return anything for this execution because we know we're not dealing with a valid cell. Once we do that, we can then mark graded RC to now be the corresponding unique island ID, right? To actually kind of avoid revisiting this current land cell in future executions of this helper function. Once we actually update or overwrite the graded index RC with this unique island ID value, now we'll actually initialize our current size to then be 1. Right, we've initialized the size as 1 because we've just found a land cell, right? That would be 1 land cell that we've just found for a size of 1. Now, this is where we actually recursively call the DFS helper function on all the 4 neighbors and add up their sizes for the current size recursively, right? So the way I usually do this for directions and recursive problems, typically in Leetcode, I'll say for dr and dc, r and c standing for row and column, and d is kind of just a standard coefficient that I've picked up over using this notation so many times in the directions array, kind of unpacking it in Python. So in directions, we'll increment the size by the recursive call of the neighboring node. So that would be r plus dr, that would be c plus dc, and that would be the current island ID. Right, so this is kind of the main chunk of this code here, the actual recursive part of this solution. Right? Again, we're recursively calling this DFS helper function on all of the 4 neighbors and adding up their sizes. Now, keep in mind, 0, 1, 1, 0, 0, -1, and -1, 0 aren't actually always going to be the neighboring cells. They're simply going to be the coordinate offsets for the neighboring cells from the current cell. Right? From the current cell, in this case, RC, in this current iteration of the for loop. And once we actually once this for loop is actually done executing once it terminates, we've actually recursively called DFS on all 4 neighbors. We simply want to return the size once it's actually been accurately incremented, right? It's actually going to store the total size of the current island, right? Because think about it. If we want to visually kind of imagine this, going back to our matrix of 1, we'd start from this one, we'd recursively explore its neighbors, which would be this guy and this guy, because those are the only 2 cells that are ones and in bounds. Then from these 2 guys, we'd recursively explore this guy, the neighbor of both of these guys. Notice how we explored all the 4 cells from this connected component, or from this connected island, and the size would then be equal to 4. And once it's actually equal to 4, we'd then simply just return 4, because that would be the total size of the current island, right? And you'd be incrementing it accordingly, right? Initializing size to be 1 in each iteration, and incrementing by 1 for each cell that we recursively encounter that's neighbor of the previous cell, and that is actually a land cell that marks that it's actually 4-directionally connected, and is part of the current 4-directionally connected island. Okay, well, once our DFS is actually done, once we've actually returned the total size, we're basically done with the initialization and the definition of the DFS helper function. This is where we actually move on to the next phase of this algorithm, where we actually compute all of the islands and actually store their sizes with their unique IDs and their actual size cells in the hash map, right? In the directions, or rather island sizes hash map. This is where that dictionary actually comes into play in this solution, right? So the way we can actually compute all of the islands and store their sizes is simply going through every single cell in the grid with nested loops, right? So let's do that. So for R in the range of n, simply the number of rows we have, and for our inner loop for C in the range of n, the number of columns we have as well, because keep in mind this is a square n by n matrix. Sorry, this should be n. For our inner and outer loops here, iterating over all of the cells, we first want to check, we only want to actually call a helper function if we even have a land cell, because we know it would actually belong to a new island. And so only if grid at the current index RC in this specific iteration of these nested for loops here, only if that's equal to 1, meaning only if it actually is a land cell that it belongs to a new island, only then would we even have to call the DFS function recursively starting from that cell RC. Now, if this is the case, meaning we do actually encounter a land cell, meaning it belongs to a new island, we could then set island at island ID, right, for our key here, and it's going to be mapped to a key value pair of the DFS call from RC, the current cell value, and island ID as our third parameter. And effectively, once we do that, now we actually called island ID on the specific RC, and we want to increment it because we want it to be unique for every single cell that's a land and belongs to an island respectively, and so we want to increment island ID by 1. So island ID plus equals 1. Sorry. Right? And basically, again, we're computing the island size recursively using this DFS helper function, starting from cell RC if it is actually a land cell, and passing in the current island ID value as the current parameter for this call. Now, once we actually do that and store its size in the island sizes hash map at that unique island ID key, then we have to actually increment or increase our island ID by 1 for the next island. Because keep in mind, once we actually assume that our island ID is currently 2. It's the very first iteration. We find a land cell belonging to a new island, and so we actually store island ID at 2, meaning it's 2, so island at 2 to be equal to DFS at RC and 2. Now we can't use 2 to be the island ID for the next island. We want it to be 3, because we want every single island ID to be unique for each island that we find that's part of a different connected component. And so we have to always increment it by 1 every single time we find a new island to make sure that every single land or every single island is mapped to a different island ID. It's always unique. It always has a unique label, and we can do that by incrementing the island ID for each connected land by 1 every single time we encounter a new island, right? That's basically incrementing the island ID for the next unique island, for the next connected component, right? Because think about it. Basically, going back to the original example here, assume we had something like this. We had 1, 0, 0, 1. Okay, sure. We'd start at this. Island ID is currently 2. We'd see this 1. It is actually a land cell. It's the beginning of a new island. We'd set island ID we'd set island sizes at 2. basically 2 is our current island ID, to then be equal to this 1, because of course the size of this specific island containing this 1 is simply 1, because its 4 directionally connected components that are in bounds are all zeros. We move on, we keep going, this is a 0, this is a 0, then we encounter this 1. Now our island ID is 3, meaning the ID for this specific island would then be 3, and it would also be mapped to 1 because it's a new island. Keep in mind, these two guys aren't part of the same island because they're not 4 directionally connected. They're diagonally connected, which means they're 8 directionally connected, but they're not 4 directionally connected, meaning they aren't part of the same island, right? That's basically the whole idea of actually implementing that unique label for each idea, for each island logic. Okay, once we've actually kind of applied that logic for each island in the hash map here, now let's actually begin the fourth phase. And before we do that, I just realized I made a quick mistake here. This should be island sizes, because that's how we initialize the hash map, not just island, of course, by itself. Okay, now, this is where we actually find the maximum possible island size. This is where we actually kind of get back to the problem statements to actually make the largest possible island that we can potentially make, the maximum island size. And to do that, the way we first initialize our max island, I'm literally just going to call it max island as my return variable. It's going to be the maximum, it's going to be the maximum of 2 different values, right? Basically, it's going to be the maximum of island, and I'll explain this as we go. So basically all the values in the island sizes hash map, and we're only going to do this if island sizes, we're only going to consider the island size value if it's actually non-null. Otherwise, it's simply going to be equal to 0. And to better explain this kind of Pythonic little line of code here, effectively again, we're initializing the max island to the size of the largest existing island, meaning its size is not 0. It actually does have a non-null or non-zero size that we can actually maximize our max island to be, right? Basically, again, when we call the dot values function, we're simply just going through all the key value pairs of a hash map. That would be the island sizes that each unique ID is mapped to. So going through all the different sizes of all the different islands in the hash map here, we'd simply just find the maximum of all of those existing islands to actually get the current max island size of the largest existing island at this specific time before actually applying that operation, before actually changing a 0 cell to a 1. Now we can actually begin the logic of actually checking for the maximum possible island after applying that operation. So again, we're going to iterate through the grid again as our second phase. Again, we do that with nested loops here. So for R in the range of n and for C in the range of n, very straightforward, simple, similar structured logic here. Right, simply iterating through each cell RC in the grid for the second phase here. But this time, this is where we only check for water cells. Why? Because now, in this second phase as such, if you will, of this algorithm, this is where we check for the 0 cells to actually check if we can possibly change them to maximize our island sizes or not. So the way we can do that is, if grid at RC, if it's a water cell, meaning in the context of this problem, it's equal to a 0, only then we can actually begin the logic for potentially changing it in this solution chunk. So the first thing that we do would actually be initialize our scene, and it's going to be initialized to an empty set. The purpose of this scene, basically it's a set that stores the unique island IDs that are all adjacent to this 0. This is kind of the whole purpose that we actually use these unique labels or these unique island IDs for each island individually corresponding to its actual size, right? So once we actually initialize that set, now let's actually again go through the 4 directionally adjacent neighbors from this current cell, right? So again, very similar logic here for dr and dc, r and c being the row and column, kind of aliases, if you will, in the directions array that we actually initialize. We'll get the new row and the new column to simply be r plus dr at each iteration, and c plus dc, getting the 4 directionally adjacent neighbors of the row and column in each iteration of this for loop here. Again, this is always going to be a for loop with 4 iterations because, of course, we have 4 different directions or 4 different neighbors to go through from each cell at any given point of time. Now, once we actually get the new row and the new row column and the new cell column, basically the new cell that neighbors the current RC cell, now we actually have to check if it's in bounds and if it actually does have an island ID that's greater than 1. And the way we can do that is basically, again, using very similar logic as, where is it? Line 8 here. Again, very similarly applying that collision logic, or rather, that out of bounds logic. So as long as 0 is actually going to be less than an r, which is going to be in bounds, meaning it's less than n, the number of rows that we have, and very similar logic for nc, as long as the same exact thing is applicable for nc, except in this case the number of columns that we have, so it's still n because n is equal to the number of rows and columns that we have, and we also want to make sure that greater than r and c, that it does actually have a island with an ID of 1, meaning it's at least greater than 1. And if that's all the case, if all these conditions actually pass, that's why we have the and keyword here, only then can we add it to our scene set as greater than r and c. And to better explain why we're really doing this in this phase of this algorithm here, again, we're simply just checking all the 4 neighbors of the current water cell, and only if it's actually in bounds and it's actually a land cell, that means it's an island that has an ID greater than 1, because of course all the IDs for all the lands, or rather all the islands, started with 2, as we saw here. As long as it has an island ID greater than 2, we can add it to scene, because of course we've just seen that island cell in this specific iteration. Okay, well, that's very simple. Once we actually add it to our scene set here, now we actually want to maximize our max island, as you may imagine. And so the way we can actually do that is simply get the maximum island again, as we initialize on line 21. It's going to be the maximum of course, itself, because we don't want to make it smaller by any means. We want to maximize its size. So max island. To the maximum of course itself. And for the second parameter that we're going to pass in, it's going to then be the new size, right? That's actually going to be the new size that we get. But there's a problem. We got the maximum island, we're incrementing it, but we're not actually we're not actually getting the new size that I'm talking about here. So what can we actually do to get the new size? Well, very, very simple solution for that. We initialize the new size. And the way I'm going to initialize the new size, it's simply going to be 1 plus the sum of the island sizes. Sorry guys, my keyboard is kind of not working today. At every index I, for every single index I in the current scene state, in the current scene set here, right? Again, with the way this new size actually works, the way it's actually being initialized, basically, if we actually flip the current cell 0, the current water cell, to a 1, the new island size would simply be that extra 1 plus the sum of all of its adjacent island sizes, kind of connecting those adjacent island sizes, plus adding 1 to it, because of course we're adding 1 to the size as we're changing the current water cell to a land cell, incrementing or increasing the current size of the islands that are connected to then be 1 greater, because we're adding 1 more land cell by changing the current water to a land cell So we'll add 1 to that result, and then actually update our max island accordingly with itself or the current new size in this iteration. And effectively, once we're done with that entirety of the solution here, once we're actually done with that, we simply want to return our max island, whatever it is, after all of the solutions, after all the nodes and their corresponding neighbors in this nested for loops here. So effectively, once they're done executing, once they fully terminate, we simply want to return the max island. Because of course, max island. Because of course, that would actually store the largest island size after flipping the most optimal water cell to be a land cell. Basically flipping the cell any one cell 0 to be a 1 in the most optimal fashion sense as possible to get the largest island possible. So if I were to submit this, unless I made any syntax errors here, this should be accepted and there should be a valid solution. Okay, let's see what I did wrong here. Give me a minute, guys. Yeah, okay. So, as you can see, really just me making very, very stupid mistakes as I normally do here. So this should actually be... Okay, I don't actually know why this is giving me an error here. If r is less than 0 or... See, again, feel forward to just fast forward this part, guys. This is just me debugging my very, very faulty code, as you can see. It definitely does work, but it is being quite weird as such today. Okay, yeah, so there should actually be an or statement here. I don't exactly know how I forgot that. If this is 0 or that's 0 or 0 or that's 0 or that. 1, 2, 3, 4. Okay, that should be right. Now this should work. Now this should be accepted. I probably made some other extra weird syntax error here. Yep, as I probably imagined. Let's see what I did wrong here. So again, I don't know why I'm actually getting these errors here. Let me just double check. Okay, so directions. It says the int object is not callable. I don't exactly know why it's giving me that error there. Okay, so it looks like I forgot a comma there. Very standard for me to do these very silly mistakes. I probably made another error here. Let's just go ahead and see what I did wrong. Tuple object is not callable now. Again, probably very similar error. Yep, I forgot the comma there as well. Let's check what else I did wrong here. Sorry about that, guys. Again, feel free to just fast forward this part. Island ID. Okay, let's see what I did wrong there. This is line 20. Okay, yeah. I think it's better if I just actually initialize this max island to be the maximum of the island size values. There it is. Okay. Okay. Now this should work. I really hope that this is actually accepted now. We'll go ahead and see what else I did wrong here. Okay, okay, so this is island sizes, not just island size. Sorry about that, guys. Let's go ahead and see if this works now. It is actually judging now, which is good. And as you can see, this does actually get accepted, and this is actually the most optimal solution for this problem here. So, sorry about that, guys. It was just me really having some buggy code here with some very, very simple, straightforward syntax errors here that I did actually get corrected. But this is, as you can see, this does work. It is really efficient, and it does actually get accepted on Leetcode. So, to kind of reiterate, how do we actually kind of overall solve this problem using this solution? Effectively, again, basically, we're labeling all the islands and mapping them with their corresponding sizes. Then we're actually iterating through all the water cells and checking how big an island can actually become if that water cell is actually flipped to a land. Right, meaning if the current 0 cell is flipped to a 1. And the final answer, which would be the max island, would simply actually store the largest possible island size after optimally switching the most optimal water cell, right? So for the time complexity here, it would actually be a relatively simple runtime complexity of big O of n squared. Why is that? Well, of course, the DFS helper function, that would run in big O of n squared. Why? Because we're actually traversing the grid exactly once. We're traversing each cell in the grid exactly 1 times with these nested loops here. And again, checking each 0 and actually calculating the new island size, basically again going through each cell exactly once, would also be a big O of n squared solution. So the bottleneck here is really just big O of n squared, and so that is going to be the total runtime complexity, because we don't really care about coefficients or constants in complexities. And for the memory or space complexity, it's also actually going to be big O of n squared, because again, we're using that hash map that we actually called island sizes here. It's going to be of size big O of n squared. Right? Because of course we're going to store at most big O of n squared islands in the worst case possible. And to actually add on to that, the DFS does actually use recursion. That's going to be using a recursive stack space. That would also be big O of n squared in the worst case without recursive calls. And so the bottleneck again would be a big O of n squared solution for the total memory or space complexity, which would be big O of n squared for both the memory and runtime complexities. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.